Yeah, so this is the last content section, which is the unsupervised clustering method. So we covered everything, and then this is really the last piece I normally cover. But after a few times, this is the 5th time I'm teaching the same contents again, and I realized, so maybe next time I'm going to actually get rid of unsupervised models, because I realized unsupervised models, it doesn't fully, so they don't connect to other sections very well in this class. So it fits much better in a data mining course, which Professor Adong is covering in much more details than we do. So next year, Professor Adong will cover more, and her class, it's mostly about unsupervised models, clustering, and there are many, many more. Anomaly detection, and which I will actually expand on reinforcement learning, maybe add 3 sections, which we're using for unsupervised model to cover reinforcement learning. But feel free to check out if you are interested in this. There are many, many YouTube intro lectures about reinforcement learning. It used to be just more like a toy tasks in machine learning, but it's getting more and more real, and it's very, very important now. All right, so again, we're doing, there's no labels, and we're just handling this matrix data with only just the samples, column as the features, and row as the different inputs. The task here is trying to figure out, so the patterns, right? A very classic pattern in when you have no labels to predict, so in the end, if you think about labels, it's some kind of guidance, right? It's guided me to look for patterns. In the unsupervised case, there's no label, and you just have to assume something. There has to be assumption, a lot of assumption you have to make to perform unsupervised models. And then the most classic we covered the last section is clustering, and this is the simplest task, is to group. So it's related to how humans think about organize the knowledge, organize the world, right? We perform, we chunk, we group things into chunks, and to make it much easier to manage, much easier to memorize. This is really related to how humans think about or manage the knowledge. So that's why grouping or clustering is a very, very basic task, because it's kind of a basic task how humans perform. All right, so we covered definition of what do we even mean group, what do we even mean similarity and distance and representation of objects, and also we covered hierarchical clustering. The most classic is the bottom up. They're a single link, complete link, or average link way to measure the distance among the clusters. And the drawback of hierarchical algorithm, which we covered in last class, was, so this is a very intuitive method. It gives you binary trees, a kind of binary tree type of organizing groups to organize all of the objects in your current data. But there's issue here is it's a very costly method. So if you do a naive hierarchical bottom-up clustering, it's n-cube cost. So then it's also like it's sometimes most cases generate more than enough because maybe what I really care is only groups. I don't even need this levels of groupings. I mean, that's just not necessary at all. So rather than having such a complete coverage of how you group the objects, let's just partition, just got bigger groups. And this is a much more computationally, much less costly task. So in the partition type of algorithms, and the most classic is kMeans. And the extension of kMeans is the mixture model-based clustering. And it normally all follows the same protocol. So you normally start from a random partition, and then you just refine it iteratively. So, so there's one important hyperparameters we have to specify about in the partition type of method is the number of clusters. And this is a very important hyperparameter, and it's very critical to get the right K, in this case, K number of groups. I'm trying to figure out how to group my object, group my samples, or group my inputs into K groups. And how do you even know K? But this K needs to be provided beforehand for a partition method to function. All right, so let's just, again, standardize the notation. So we have n input. I want to group it into K clusters, and each input is described by P features. And the reason why I try to standardize the notation is just to compare with hierarchical clustering later, and to see if this is indeed computationally more efficient and less costly. So P, so each object is represented by RP, for example, and then there are total n inputs. And you want to group them into K groups, or K clusters. All right, so very simple, like if you are given this type of maybe nodes, they're geometrically represented in this two-dimensional space, very, very naturally you can group them into 3 clusters just based on density. So this is one way. The other, like this, when you're given this type of data, for example, this is age versus salary, or age versus the assets. And then normally when you have more older, you got more money, but there's some kind of like not in a cluster point, like a lot of people very old, but they don't have money, or there's a group of people has very young, but they have a lot of money and inherited. So those naturally makes this into 3 groups. So, so that's just how partition cluster work. So, and based on this, you can actually tell, I mean, there's something very important in this kind of cluster is, first is, we normally have this kind of oval shape. We assume this oval shape. And what do oval shape even mean? In fact, this is just a Gaussian distribution. You're assuming a Gaussian distribution in this cluster. And we actually revealed what do we even mean Gaussian distribution, right? Whenever this Gaussian distribution, what you care is the center and the covariance shape. So after we talk about kMeans, and then the Gaussian mixture model, this is a very classic Gaussian mixture model based clustering. Sorry. What you care is, so sorry. Yeah, so what you care is the center. It's mu sub k. K from 1 to capital large K, and then sigma k, which is the covariance, measure the shape. And then also there's another is, what's the proportion of each of the cluster? And this is the biggest cluster, this is the second biggest cluster, and this is the smallest cluster. And this is also some information about the cluster. We'll get clear in the future slides, but let's start from the simplest clustering, partition clustering ever, which doesn't even consider the covariance at all. It only considers the center. So that's called kMeans clustering. The kMeans clustering is like the simplest partition method ever. So in the end, I'm trying to group my objects into K groups. And so how could you get the best partition ever? So there's one way we talk about in the hierarchical clustering, we can just enumerate all the possible clusters. and then we compare. So which of the clustering give us the minimal within cluster similarity, and then maximize the between cluster similarity. And you can just enumerate all the possible clusters. And however, but that approach requires to enumerate how many kinds, because for each data point, you have the choices to be in the cluster 1, 2, until k. So for every data point, we already standardized notation, right? You have total n objects. How many possible partitions? When you have n objects partitioned into k groups. Very easy. K power to the n. And this is exponential, and this is just too costly because n is normally larger than 100, right? Even 2 to the 100 is a very, very, very big number. So let's just roughly count. 2 to the 100 means I'm trying to group 100 objects into 2 groups. And this is already a very, very costly if you do total brute force enumeration. So, and then people converted it into a heuristic-driven method called kMeans. So there's actually a reason why performing kMeans, but let's just for now think about its greedy method, heuristic-driven greedy method, because enumeration is just too costly. Yeah. So the kMeans method is, so the user pick a k and randomly pick k points as the center point to start. And then decide all of the n objects, all of the n inputs, which one of the center from that k cluster you just randomly chose is the closest. Then you think this point belongs to that closest center. After you assign every point into one of the k clusters, and you recalculate the center just using a min operation, and then this gives you a new set of center. Then you redo for each point, you try to figure out who is the closest center. And you just do it iteratively again. If none of the objects change the membership in the last iteration, then you actually just, this kMeans stops. So this just like a pseudocode, let's just see the careful example run. Okay, so I have all those blue inputs in this two-dimensional space. And I want to group them into 3 clusters. Why 3? I picked 3. For now, there's no reason. I picked the 3. I want to group the points into 3 groups. And I don't know where are the 3 groups. I just randomly put those 3 centers to 3 random positions. So now, I need to decide each point, are they belongs to the first group, second group, or the third group. And very easy, I just use distance to measure. So is this center more close to me, or this center, sorry, it should be a straight line, or that center close to me. And very simple, and whoever is the closest, I belongs to that cluster. So for this one, it's super easy, right? So it should be K1. Now let's see, K2, this is the other points. Measure K1, K2, K3. Looks like this point belongs to K1 too. But it's in fact, I mean, we know to know how the points in the space, in the two-dimensional space, belongs to a cluster. There's an easier solution is we just connect this K1 and K3, the line perpendicular to the connecting line, and also past the center of that line, separate the space. It separates the space into, maybe slightly. So, it's just basic geometry, right? Whoever on the upper, it's more close to K1. Whoever is lower, it's more close to K3. And then you can just do this for every pair. K1 versus K2, separate the space. It's very easy. I mean, through this middle line, perpendicular. I think it's right, but not entirely. Yeah. And then K3 and K2 do the same separation. Then, in fact, if you look at this, the three lines, there's a little bit, not entirely good, but that's just roughly. The three centers actually separate the space into mutually exclusive sections. And if you learned it in the algorithm class, this is called a Voronoi diagram, right? Just mutually exclusive partition of the space. So each set of K centers provide one Voronoi partition. Okay, so now I know this partition. I'm using this in the points within my current cluster to recalculate who is my mean. And very clearly, this K1 should be shifted to be more close to the right? Because most of the points are more close to here. The center, of course, should be more close to the right. And the K3 should be a little bit moved up because there are more points on the upper right. And this K2 very clearly should be more on the right, left. So that's how you recalculate the mean, and then you get the second round of the new center. Okay, so after you get new center, then you need to repeat the whole process. I need to decide, is this point, especially this point belongs to the K1 or K3? So actually you can tell because K3 got moved to here, and this point, even though it was belonging to the K1, now it clearly should now belongs to K3. So because of this is an iterative process, you are reassigning the membership, and after the membership got decided, you recalculate the mean. And then you need to do this iteratively again. Okay, question about this? It's a very simple method. Yeah, so, and then you do it, and then this point is shifted to, and then the second round, this got blue, and more. So every time you have to decide for each xi, this is the first step. For each xi, which is my center? It's a K1 until K3. And you need to perform this distance measure calculations, right? Center versus E points, and there are total K points to decide. So we're going to do this later, and then you do an argmean of the current points versus all the centers, and then use the best as my current center. That's the first step. So all right. And then the second step is to recalculate the center, which is actually here. The second step is to recalculate the center. I should swap the two pages. So membership assignment and the center calculation. The center calculation, you can tell it's it depends on how many points are here, and you perform a summation operation, and then you divide it, normalize it by the size of the cluster. Roughly, so the cost of this is, so what's the cost of calculating a mean operation? So, of course, this depends on the size of the cluster. And then you just perform a summation and then scalar division. But if you consider every point, so in the end, you need to perform a summation of endpoints, right? Total endpoints, sum, but even though they are not summed into one cluster, they're actually summed into k different clusters, but the number of summation operations are On. And because each of the xi is a p-dimensional feature vector, this step's cost is, I think it's ONP. Question about this? Yeah, it's a very, very simple operation, right? Sum. Just summation. And there are p elements to sum. Yeah, it's OMP. All right, and then let's see this operation. Assigning the clusters, what's the cost? So for each of the sample, for every I, and there are a total of n objects, right? For each object, you need to calculate the distance of that object versus the k clusters. And each one of those, let's assume that's Euclidean distance. Each Euclidean distance calculations is OP because there are total n p elements. So kj versus xi, and then for each object you have OKP operation, right? So this is OKP for each, and then you need to perform this membership assignment for all the objects, which makes the total computation is comments or concerns about this? Yeah, because for each object, you need to perform this distance calculation versus all the k clusters. That makes OKP. And then this is only for one object, right? You need to perform this operation for every object. There are a total of n objects, so that's why this is ONKP cost. All right. Okay, so again, so this is the Voronoi diagram. It's for each set of key centers, the fixed centers, the partition the whole space into k mutually exclusive subspace to form a partition. And then this is known as Voronoi diagram, and then you change the position, and changing the position of k center leads to a new partition. So let's actually perform this even more because this is such a simple method. I want you to do it again. So, okay, so we start, for this case, actually to be honest, we don't know it's k to 5, but just visually use your eyes. Oh wow, 5 makes sense, right? You pick 5 centers, but the starting of the key 5 centers actually are very badly positioned. And you randomly guess the key center positions. Those are the red points. I hope you can read the red points positions. And then you just assign, there are actually much more points now. They're pretty densely located. And then using that k different centers, you can partition the whole space into this. And then you recalculate into each position the new center. Very clearly, this center will move up, and this center may be a little bit up, and this center will be a little bit left. And then, yeah, so that's the second round of center. Then you're reassigning the, you jump to the new center, then you're reassigning and to get a new partition again, and many times until this reach its final convergence stage. And hopefully it reaches the convergence state. And actually it will. It always will converge. A very good property of kMeans is the convergence is guaranteed. Question about this? All right, so, here I just emphasize again, so computational complexity is, this is actually, next page. So we already covered, right? So OKNP is about reassigning cluster. ONP, it's ONP, it's the recalculating the center. And you also have 2 times because this dominates this. So kNP dominates the NP. So in the summation, because this is iterative, right? It's a summation relationship. And the dominating cost is reassigning the center is the dominating cost. And then you don't do it only once. You actually do it many, many times. Assuming L times. L, and then the whole cost is O, L, K, and P. But there's a good thing is, so let's compare this to hierarchical clustering. So if you remember the hierarchical clustering is N cube P. And let's look at this number. N cube versus L, K, and N. So because they both have an N, it's canceled out, and then really the comparison is N quadratic versus LK. So you always has K much smaller than N, right? Of course, and this is a clustering. And then it depends on L, right? L is normally much smaller than much smaller than N2. It actually kMeans converge very fast. So this is a much smaller number for the normal size of the objects, and that's the reason why the kMeans it's a much computationally efficient method, less costly method compared to the hierarchical clustering. Question about this? And also the K is what you define, right? You decide. K is, if you in a normal algorithm setting, K is a constant. I can even cancel K out. It's only a constant. It doesn't grow with my data. Which makes the whole method actually depends on L, the convergence number of iteration. And kMeans, in fact, is a special case of a method called expectation maximization. EM method is guaranteed to converge. In the most data, it converges very nicely. And there's an extra slide about EM, and you can just read it. All right. So so here I copied the hierarchical clustering we had before. So feel free to do 1 versus 1 comparison versus the kMeans versus the hierarchical clustering. If you still remember, the bigger cost in the hierarchical clustering is you have to calculate this matrix. This is called a rematrix calculation. And then when you have the matrix, you need to calculate the best cluster for my current stage, right? So the majority of the cost actually, in fact, it's it's in the recalculating of the pairwise distance matrix. This is the dominating cost. And this is an quadratic, and because the hierarchical clustering, you have to do so the bottom-up version, you have to do many times to group all the objects into one cluster, which makes the number of merging operation is proportional to the n. So that's the reason why there's an n quadratic cost in the matrix calculation, then there's n total of re-matrix cost, re-matrix iteration. So that's the reason why actually you need to have, if doing naively, it's an n cube cost. So this is an n quadratic. For each, there's the best cluster, it's almost open quadratic. And then you also have cluster n minus 1 merging operations in, and that's almost like iteration in the kMeans, right? And this merging operation in hierarchical clustering grows with the n, which is also a very big differences versus kMeans. So that's the reason why the naive method is n cubed times p. I should write p there. Yes, this is actually p. Yeah. All right. Question about this? Oh, this is too confusing. Yeah. So you can actually tell I really like to do time complexity analysis of method we learned. The reason is I feel, so in the end, machine learning, it's more, it's a hot pot for handling data, right? There's all those different kind of properties you add on top of the method. You either add, you make it faster, that's one way to make it better, or you make it more robust, that's another way to make it better, or you make it more fair, that's like a third way to make it better. And as a computer science scientist, what you learn a lot before is, data structure, coding, and algorithmic solutions. Those all equipped you with a very good direction is to make it the machine learning method more actually faster, because the things you learned, it really equipped you with the skills. But how do you make it faster, right? You have to analyze it first, right? You have to understand who's slow, who is not slow. And that's the reason why I kept trying to analyze all this and also compare. But of course, this is only just one perspective to analyze all those methods, right? There's another perspective. So if you are statistically trained, you got a lot of training in probability, in mathematics, in basic math. And then those type of skills will help you understand are the function you want to learn truly matches the data better. So that's the reason why in the statistics field, they actually have a big focus on error bound analysis, right? Because the skills they learned equip them with those necessary tools to help them to analyze those. Later if you try to, in your research or maybe in the jobs, you have to consider what is my niche? What have I learned before? It's something needed, something necessary, or something can be improved. It's my niche, even can improve something of this, the thing I care. So if machine learning is what you care, think about your niche, your skill sets. Is your skill set algorithmic analysis? Then scalability is a very good direction. If your skill set is mathematics or information theorem or statistical analysis, then theoretical error bound analysis are good direction for you to improve. And then it's really in the end, so there's a reason why I'm doing this, because I feel like the majority of the students here are more computer science oriented. So maybe scalability is your niche. You think about you're going to work in your future jobs and how to scale up some simplest method into many, many data. And doing this type of analysis is the first step to realize, okay, is some parameters, some variables are the bottleneck, to hinder that method to scale up, right? So I hope this, whatever analysis I did before, give you a sense of this type of research. And I hope you understand why this cube P. And I can repeat this because I really want you to get it. Okay, so if you still remember what is hierarchical clustering is you have a pairwise distance matrix of all the data points in your data. So this is already much more computationally costly than kMeans, right? In the kMeans, what do you even need to do? You only need to calculate every point to the center. You only need to calculate every point to the center. And there's only k centers. But in the hierarchical clustering, you have to calculate every point to all the other points. And this is already much more computational costly. Okay. And then the recluster has a little bit, so those are more details. So after you know the best cluster, in this case, you group 1 and 2 together. And then your current cluster is 1, 2, 2, 3, 4, 5, right? And then you need to rematrix this old matrix into a new matrix. And to calculate the cluster 1, 2 versus 3, 4, 5. Because that's a new cluster. You have to recalculate this distance, right? And then because of the size of that cluster, it's upper bounded by ON. And then for the rest of the points, it's also upper bounded by ON. Equivalent to, I'm calculating 1, 2 cluster, this size N versus, this is really what I wrote here. So I'm trying to calculate this new cluster, treat it as a new point. This point versus all the rest of the points, the distance. And if this is only a point, the calculation is very simple. It's just the point versus the other points, right? But the problem is this is a cluster and it's size N. No matter what single link, complete link, or average link you're doing, you have to calculate 2 versus 3 to 4 to 5, and 1 versus 3 to 4 to 5, and then compare. The single link is to get the smallest, complete link is get the largest, average link is get the average. So in the end, you have to calculate this versus everything from the rest. And this size is upper bounded by ON, and this size upper bounded by ON. This is a pairwise combinatorial operation. That's why reclustering cost is ON quadratic. And then you have to do this rematrix operation for n-1 merging operation, because you want to merge everything into one thing. It's just, the more data you have, the more merging operation you need to conduct. So that's the reason why it's hierarchical clustering, just intuitively, it's much, much more computationally costly than the kMeans. All right, okay, so enough for this, and then let's now see why kMeans converges nicely. So from the beginning, we talk about what makes a good cluster is we have an intuitive definition is want to maximize the within cluster similarity, want to minimize the between cluster similarity. And how do you even represent it in the grouping case, right? So in the kMeans, it's actually very, very intuitive because we're trying to minimize points versus the center distance. And that's really just, so I'm now, because I need to represent center, right? So now let me use notation C to represent each center. And then the distance is each xi minus the center, and then take a quadratic. It just, in this case, it just, Euclidean distance. And then there's an indicator function called Mij you need to introduce. It introduces just the cluster membership. If the points belongs to C1, that notation equals to 1. If the points doesn't belong to the cluster, that notation equals to 0. So this really just shows what's the within cluster similarity measure, and then sum over all the clusters. If the points doesn't, assuming let's use a point as example, so this specific point, it belongs to C2, it doesn't belong to C1, so that's why the I is so this is the xi point, mi1 equals to 0, mi2 equals to 1. And it's really just the contribution of this point into that cluster is 0 because it's not in the cluster at all. So it's just equivalent to I only just sum whatever points belongs to my cluster, and I'm summing over all the clusters together. So this is a very intuitive definition of within cluster similarity. I'm trying to within cluster similarity, then my goal is to minimize the within cluster similarity. But from the beginning, what you are given is only just X. You don't have anything else, right? You have only X. You don't know C, you don't know M, and those are the parameters you need to search. So my goal is minimize the within cluster distance in this case, and then it's represented by this function, and then there are two sets of parameters. The first parameter to look for is the center. The second set of parameter is the each point's class membership assignment, which is M. So, and now, okay, we're coming back to what we started from the beginning, right? Every machine learning method can be written as a loss function, and we are minimizing a loss function. We are minimizing within cluster distance in this case. But our parameters, our unknown parameters are much more complicated, which is C sub G. There are a total of K C sub G centers to look for. There are a total of, actually Mij is N times P. This is a matrix. M here is actually a matrix. It's N times actually K. M is a matrix. It's N times K matrix. If you write it as a matrix form, is the first I is N, and then the second is K. So this is my parameter to look for. There are N times K parameter to look for. And you actually can do that very easily. Again, our old trick. Set it to gradient as 0, set the loss function versus one of the parameter partial positive, partial derivatives at 0, then you solve it. The issue of this two sets of parameter is, okay, so the solution, if you do this partial gradient, partial derivative as 0, the C parameters uses M in its solution. And the M uses the C in its solution. Because both C and M are unknown. There's no way if you just directly solve it, because C uses M uses C. And there's no complete solutions at all, because I don't know M, I don't know C. And then what can you do? And then the solution is, okay, let's do an iterative fashion. Let's assume M is known. When you assume M is known, you can solve the C. When you assume C is known, you can solve the M. And that's actually solved the whole iterative solution. But you have to assume M is known or C is known, right? And then that gives you the solution, which is iterative kMeans. So in the beginning, because of these two sets of parameters are correlated, you have to know one part to solve the other part. And that just gives you the solution has to be an iterative method. And you assume the center unknown, and then you solve the best solution is exactly the current kMeans solution. Okay, I know the C, I know the center. When the center are fixed, each point, the cluster membership is whoever is the closest, whichever center is the closest to this point is the membership assignment, which exactly is the assignment stage in the kMeans. And when the M is known, which is the state, right? Okay, you assign every point into a certain cluster. And now when you know the membership, the best class center is just whoever belongs to that center, the mean, which is exactly the solution. If you look at the solution is, the upper is Mij times Xi over the summation of Mij. So this is, the upper is whoever, because Mij is a binary variable, right? Whoever doesn't belong to the J's cluster, the Mij will be 0, right? And then this makes what? The upper is only those points belongs to the J's cluster. You just sum them together. And the lower is whoever doesn't belong to the current cluster, it gives you 0. And only those belongs to the cluster give you 1, right? This is exactly the size of that cluster. And this is exactly in the step of kMeans is calculating the mean operation. So, and the whole thing I could give you, kMeans is not an arbitrary method. In fact, it's a method just because the membership and the centers are correlated. So that's why we're trying to solve this loss function through because of the two correlated parameters. We have to solve it through an iterative method. All right, question about this?
But there's only, and the reason why it converges, it's because you're using Euclidean distance, right? And there's only one global optimum.
Good question. So the question is it because we use Euclidean distance, that's why it converges? Actually, no. The reason why it converges is because this is a special case of a method called EM. And EM is proved to have good convergence behavior. And that's actually related to some much more complicated concept I covered in the lecture 19b about the EM. So feel free to check it out if you want to read EM. All right, so kMeans is a special case of expectation maximization algorithm. EM is known to converge, and the number iteration could be large, but in reality, it depends on your data. And in most cases, it actually converges pretty fast. All right, so this is about the theoretical, a little bit theoretical analysis about convergence and k-means. It's not like hierarchical clustering. We don't have a global loss function to optimize. Actually, in the k-means case, we have a global function to optimize. But the specific optimizer is an iterative method because there are two sets of parameters and the parameters are correlated. And you have to use an iterative method. Okay, so so this is actually about convergence. I'm going to skip it. Feel free to read why. It optimizes a goodness measure. So you can actually prove it monotonically decrease that goodness measure, and so feel free to read the previous proofs. Okay, so now the question is, how do you pick the starting position of the clusters? The seeds is actually somewhat critical. So people normally just use random restart. You can have multiple rounds of restarted, because in the end, EM doesn't converge to global solutions. It's a local solution. It's an optimizer, give you local optimal solutions. It doesn't guarantee give you global optimal solution at all. And this means what? If you started from a really bad starting point, it might converge to a bad local optimal solution. But this is kind of similar to stochastic gradient descent, right? We had that kind of issues before. The starting point is somehow critical. But it's easy to solve. You just restart. You do random restart for a few times. Okay, so to summarize, k-means just perform the basic grouping operation. It just partition the group into multiple groups. It has this assumption called a mixture of spherical shapes. So this maybe sounds kind of magic now. We're going to talk about in the next few slides. The basic assumption in k-means is it's a spherical shape. It doesn't consider the covariance of the oval shape at all. It's a sphere. The basic assumption is each center, each cluster is a sphere. And the loss function you are optimizing is sum of a square distant to the centroid. And the method is an iterative method. It's a special case of EM. And then the model is the cluster membership and the centroid, which is represented as Mij and Cj. And their Mij is n times k matrix. Cj is each Cj is a p-dimensional vector, and there are a total of k Cj vectors. All right. Okay. So then the simplest question now we need to ask is how to pick k. So actually, it's very difficult to pick the right k. So there are many approximation methods. So let's just introduce one of the methods. So when k equals to 1, you got this that objective function, right? Summation of distance to the centroid. And then you can keep adding k, make k bigger. And there's something called knee finding or elbow finding. It normally has this drop of the objective function, and then it reaches a plateau. And you can think about that plateau stage means it's not improving anymore, and this knee point is the best point. So intuitively, it's a good solution. It's an okay solution. So in the homework, if you want to do the actual credit, it's actually pretty easy to use the knee finding or elbow finding to figure out the right k. Question about this? And just to let you know, this is a very easy case. So that's why you got a very clear plateau, a very clear drop, and then the plateau shape. But in a lot of real problems, it's not as clear as this. Sure.
Generally, we kind of like see this from the graph and interpret it, right? So there is no like mathematical formula to find the knee or something.
Yeah. So how to find the best K, right? The question is, are there mathematical methods? There are actually a lot of methods proposed. So for the classic maybe topic model, if you think about what is topic modeling. Topic modeling is group the documents into topics, right? And how many topics? And there are a lot of Bayesian type of method. So adding the directly prior, I don't want to talk to the rest of the class. So there are a lot of Bayesian type of method being proposed to figure out the right number of clusters. There are a lot of prior type of probability formulation. There's something called Indian buffet process or Chinese buffet or Indian restaurant. There are many prior type of probability function proposed. So it's a huge it's a huge topic. How to figure out the right number of clusters. Yeah. All right. So again, so even if you already got a K, you have a good elbow or good knee positions, but you still need to measure, right? How to measure the final clusters, and actually it's very similar to what we had before in the decision tree of the final leaf nodes. So what makes a good leaf node in decision tree? As pure as possible. In a clustering case, it's similar. If you know the labels of the clusters and you want to look for those clustering results as pure as possible. That really just, there are many different measurements you can use, even the Gini and entropy or the specific called purity method we can use here. It's very simple. It's you really just use the maximum number of that cluster over the total size, and it shows how pure is my current cluster. And consider all the cluster, you sum them together. This is only one choice. There are many possible other choices we learned. It's a similar task. It's a very similar measurement as decision tree, the leaf picking. So yeah, so this is purely easy. Let's just see the purity of class 1. We just see, we do assuming, so here in the end, the first question is, how do you even know the color? The color here is actually, you know there are class labels. And this sounds pretty odd, right? So you already know the class labels, why do you even cluster them? Why not just learn a predictive model to directly predicting? So there are a lot of arguments actually in the literature about, so some researchers think this kind of unsupervised method is can maybe learn more than predictive models, but you can use those class labels as a validation of the cluster outputs. So that's a lot of arguments from that crowd. I'm not completely agree with those because I'm more in the predictive tribe. So in the end, you can tell I always feel clustering method, it's a very subjective operation. And you can use those more like a filtering type of operations. But it's just in the end, the most difficult part of clustering is how do you even know the quality of clustering? It's extremely difficult because you don't really have a good measurements at all. And in the kMeans case, you minimize that summation of the points to the cluster center, but there you actually have a good assumption is Euclidean distance or whatever distance measure is a good measure. It's very questionable is that that's a good measure if you have certain goals in mind. But so for the homework, you just use this. I mean, you can also use Gini if you know how to calculate Gini. It's the P times 1 minus P. It's also a very good measure. All right, so we have only 10 minutes. I don't want to cover too much about Gaussian mixture models. I will just do really quickly. So feel free to check out lecture 19b about Gaussian mixture models. I will only cover the basic version here. Okay, so what is Gaussian mixture model? So for Gaussian mixture model, in the end, you're assuming each cluster are generated from a specific Gaussian distribution. So this is a Gaussian, this is another Gaussian, this is the third Gaussian, this is the fourth, this is the fifth. And we already learned, right, what makes a Gaussian distribution. A Gaussian distribution just needs to know the center and also needs to know the shape, the covariance matrix. And if you know the center, in this case it's mu sub j, so j from 1 to k. So it's very similar to kMeans. So in the kMeans case, you only need to calculate center, but in the Gaussian mixture model case, you need to calculate the covariance. That's the only thing actually more. There's actually a little bit more is we're going to talk about later. Is more than the kMeans is it's not just about center, it's also about the shape. And the shape is represented by covariance matrix. Now, because of this, you can reflect what kMeans really is about. In the kMeans, we don't care sigma at all. And we only care about center. It has this implicit assumption is this Gaussian distribution is a rounded circle, or in the multidimensional case, is a sphere. There's no kind of stretching or thinning type of shape at all. It's rounded. It's a round sphere. Okay, so now let's see what's Gaussian mixture model. And the basic method to train Gaussian mixture model is expectation maximization. So you start guessing the centroid and covariance of each of the K cluster. So now your guessing is not just the center, you also need to guess the shape. And also beyond, you also need to guess the proportion of the cluster. So there may be dominating cluster, there are smaller clusters. You also need to have a parameter representing how did each cluster dominating the points. So maybe from the beginning you can just assume the probability of each cluster is uniform, 1 over k. Okay, so now you have this starting point, and similar to the kMeans, for each point you need to assign who is my cluster. It's very easy. I mean, for each point you trying to calculate for that specific point what proportion of my points belongs to cluster 1, cluster 2, onto cluster k. And this is a very different step compared to the previous step. If you remember kMeans, in the kMeans, we trying to estimate Mij. I is for xi point. It's equals to 1 or 0, right? So if the xi belongs to the center j, it's 0, it's 1, otherwise. However, in the Gaussian mixture model, this Mij is not a binary variable anymore. It becomes a proportion. It's trying to measure what proportion of the data points belongs to first cluster, second cluster, until the case cluster. After you doing the assignment, this is called a soft assignment. In the kMeans, it's called a hard assignment. And in the Gaussian matrix model, it's called soft assignment. It's proportional. And after you're assigning the membership of each point to the clusters, and then you recalculate the mean and recalculate the variance, which almost the same as the k-means, you only recalculate the means. So let's use an example to show this. All right, so we start from this point located there. I'm just randomly guessing there are two centered, and also the covariance is kind of rounded. So I'm guessing my cluster center exists here and there, and also they are very nicely a circle shape. Both clusters are circle shape. Okay, so now I'm trying to assigning all the points into the cluster. So you actually can, so roughly here, I don't show the proportion of each point to the different clusters, but just roughly, all the red points are belongs to the red cluster, all the blue points are belong completely to the blue cluster. And now you are re-estimating not just the center, but also the shape. And this gives you a very stretched out, very stretching type of oval shape, right? And this is the new red cluster, this is the new blue cluster, and then you recalculate the center and the shape, and then for that new center and shape, you're trying to assigning the membership again, until the end. The cluster estimates both the center and also the shape. So this is more than k-means, because it measures the shape of the cluster. So this figure shows you the shape is also important. Okay, so this is one demo. I want to show you a different demo, which is actually a true Gaussian mixture model. Because the previous demo, each point, it seems to be completely belonging to the red or the blue, right? But in fact, the true calculation in Gaussian mixture model is you split each point to thinking how much that point is generated by the green cluster or the blue cluster or the red cluster. So this is the starting point. And you have a red cluster, which is kind of stretched out shape and has a really round oval shape. And the green cluster is nice, rounded, green cluster. And the red cluster, the blue cluster is even more stretched. It's even outside the whole page. It's very stretched out. And there are also this number called P equals to 1/3. Just trying to show you each cluster is the proportion. They are uniformly in the beginning. And now you're assigning each point into one of the three clusters softly. It's not hard. It's not yes or no. It's proportion. So you can actually tell the points, most points here, because it's actually very easy to check this. So when a Gaussian mixture model is so thin, it means what? When a Gaussian mixture model is so thin, we actually talk about it. Well, a Gaussian mixture model is so thin. So again, Gaussian mixture model, right? And that curve shows you in this direction is 2 sigma, right? This direction is 2 sigma. And we actually talk about it, whenever it's more than 2 sigma, likelihood is 0, right? When it's outside the 2 in this direction, the thin direction, really narrow direction. So this direction is very centered. It's very centered around the center. Just a little bit off among the direction will be very unlikely. This makes what? It makes all the points here, of course, they're mostly belonging to the green cluster, because this is so narrow, the blue is so narrow, and the red is also so narrow around that direction. So that's the reason why all the points here are mostly belong to the green circle. because that's the most likely. And then the points are more on this right side, and then it's difficult to know. It may belong to the green cluster, it may belong to the yellow, the red, or the blue. Okay, so now you assign each point softly into each cluster. Now you start to recalculate the new center and the new shape. And just after one round, your green cluster becomes more, there's a shape now. It's not a fully circled, fully rounded. It becomes more banded in that direction. And then the red circle becomes clear and the blue circle becomes a lot smaller. And then you're just reassigning all the points again based on the new center, new shape, and new proportion. You can tell the proportion also revised. So the blue one is 0.221. The red is this is the red. Red is 0.27, and the green I think is about 51. So the green point is a dominating cluster. I mean, that three number represents the ratio. And then you just keep doing again. And this gives you a much better density estimation about, so this is the proportion, and then you got, so until it reaches the stage, most of the points are dominated, controlled, generated by the blue points, red points, and green points. And also there's a reason now you tell why this point belongs to the red, not belongs to the blue. Because, let's see, if using the kMeans, this point will very clearly belongs to the blue, right? But actually based on Gaussian mixture model, this point belongs to the red mostly, because in the end, that red cluster spreading over much more in this direction. So there's much more likely to generate the red versus this blue clusters. So it's capturing not just the center, but also the shape much better. All right, so just 2 minutes, Gaussian mixture model are very famously used for speaker audio analysis. This is the dominating method before the deep learning method. It's, if you know IBM speech recognizer, it's dominating the market before 2012 for almost 20 years. It's a simple method. You only just assume each speaker is a Gaussian mixture model. You calculate the mu, covariance, and also proportion. And then in fact, for each Gaussian mixture model, this is the parameter you need to estimate: proportion, center, and covariance. And then you have a total of k, maybe speakers. And then this is the whole thing you need to estimate. This is a much smaller and efficient model, and it's actually much smaller compared to the state-of-the-art deep learning models. But it's extremely effective and has solid performance in audio analysis. All right, I think that's it. So this is the last page, Gaussian mixture model, mixture of Gaussian, and then actually what you're optimizing is likelihood. You check out the lecture 19D about EM and also C, and